In early times, the famous scientist Leonardo da Vinci had the right idea about the theory of flight, but he lacked enough power to propel his helix through air. Other early scientists such as Chanute and Lilienthal solved many problems relating to lift and control, but without power, their gliders were only steps in the right direction. It wasn't until the power plant was invented that flight became a reality. This enabled the machine to move through the air fast enough to produce the necessary lift. As a result, progress in flight closely paralleled the development of the aircraft engine. Therefore, knowledge of the modern aircraft propulsion system is one of the most valuable assets that you, an aircraft maintenance technician, can possess. To help you gain this knowledge, the following two-part presentation has been prepared concerning the basic principles of aircraft reciprocating engines. In part one of this program, we will discuss the transformation of chemical energy into power, the evolution of the aircraft engine efficiency, factors which affect engine power, and engine monitoring instruments that affect engine performance. In part two, we will consider each of the 7 basic systems of an aircraft engine. To begin with, the main purpose of an aircraft engine is to convert chemical energy contained in the fuel into thrust or mechanical energy which moves our aircraft through the air. This is accomplished by releasing the chemical energy locked in the fuel by first changing it into heat and then into mechanical energy in the aircraft engine. This is why an aircraft engine is called a heat engine. We use the resulting power to turn the propeller which produces thrust. Petroleum-powered engines, from the tiny ones that power our chainsaws to the huge jet engines that propel our largest airliners, are all considered heat engines. All of them operate on the following basic 5-event cycle. The first event in the energy transformation cycle begins when a combustible fuel-air mixture is taken into the engine. Secondly, this mixture is compressed to pack the greatest mass of chemical energy into the smallest volume. This compressed mixture is then ignited and burned, releasing energy in the form of heat. The air inside the engine immediately absorbs this heat and expands to many times its original volume. It is this expansion that is converted into mechanical power. Finally, after the energy has been extracted from expanding gases, these gases are expelled from the engine, and the cycle is ready to begin all over again. In a modern turbine engine, these 5 events all take place at the same time in different locations within the engine. First, the air enters inlet ducts. It is then compressed by the spinning compressor. Fuel is sprayed into this compressed air in a combustion chamber where it is burned to expand the gases. Finally, these gases leave the engine through the tailpipe. The thrust produced by a turbojet engine is caused by the accelerated air passing through it. The greater the difference in speed between air entering the engine and air leaving the engine, the greater will be the thrust. The modern turbine engine has gained in popularity over the years as a primary source of power for our large, high-speed aircraft. But the reciprocating or piston engine will be around for many years to come as the source of power for our smaller, short-range aircraft. For this reason, we will concentrate our study to the operation of this engine throughout this program. While the 5 events of energy transformation in a reciprocating engine are the same as those in the turbine, there is one major difference. All events in a reciprocating engine take place at the same location, inside the cylinder, but at different times. There are basically two different event cycles used in reciprocating engines: the two-stroke cycle, which is simpler and less efficient, and the more commonly used four-stroke cycle. The main difference is the same 5 events take place in 2 piston strokes in a two-stroke cycle engine. Here the expanding gases force the piston down and turn the crankshaft. Near the bottom of its stroke, the piston uncovers the exhaust ports, and at this time, the intake valve opens, allowing the incoming fuel-air charge to force burned gases out through the exhaust ports. Continued rotation of the crankshaft moves the piston above the exhaust ports, and when the intake valve closes, the mixture is compressed and ignited with a spark plug just before the piston reaches the top of its stroke. The heated, expanding gases then force the piston back down on its next cycle. The four-stroke cycle engine was developed and became the one used in aircraft due to the inefficiency of two-stroke cycle engines and the difficulty of cooling caused by its firing on every stroke. In the four-stroke cycle engine, 2 valves are timed to open and close at specific crankshaft positions. This allows the fuel-air mixture to enter the cylinder and the burned gases to leave it. The first stroke of this cycle begins with the piston moving down, which opens the valve. The fuel-air mixture is drawn into the cylinder from the carburetor. Then the intake valve closes, and the piston moves up on its compression stroke. This compresses the fuel-air charge into a very small volume. Near the top of this stroke, an electrical spark ignites the mixture. As this mixture burns, the piston reaches the top of its stroke. This builds up the maximum amount of pressure in the cylinder. This pressure forces the piston down, creating the power stroke. All of the work performed by the engine is done on this stroke. Finally, the exhaust valve opens, and as the piston moves back up, the burned gases are forced out of the cylinder to prepare the cylinder for the next cycle of events. Now that we understand the basic principle of energy transformation in a heat engine, can you name the 5 events that take place when chemical energy is converted into power? The fuel-air mixture is taken into the engine. This mixture is compressed, the compressed mixture is ignited, the burning mixture expands the gases in the engine to perform work, and burned gases are expelled from the engine. Also, can you name the 4 strokes of a 4-stroke cycle engine? Intake, compression, power, and exhaust. The evolution of the airplane from the Wright Flyer to the high-speed, high-altitude business aircraft is no less amazing than the evolution of the engines that power them. For example, the engine built by the Wright brothers in their bicycle shop was a 4-cylinder inline engine. This engine lay on its side on the wing of their Flyer. It weighed almost 200 pounds and produced about 12 horsepower. 14 years later, during World War I, a popular engine called the Curtiss OX-5 was developed. This was a 90 horsepower water-cooled V8 engine that weighed almost 450 pounds. About this same time, the best engine of the day was developed in France. It was a rotary engine that actually spun with the propeller to produce the needed lightweight power to propel the flimsy pursuit airplanes. The next logical step to engine design was to hold the cylinder still and turn the propeller by means of a crankshaft. This gave us the first radial engine that offered low weight for its horsepower, but at the same time required a rather large frontal area. Through the years, Lower power requirements were met with 3, 5, 7, or 9-cylinder radial engines. Ultimately, however, higher horsepower engines were developed by using 2-row engines with 18 cylinders, or even 4-row engines with 28 cylinders. Today, when power in excess of 400 horsepower is required, turbine engines, either turbojet or turboprop, are used. This is because their weight-to-power ratio is so much better than that of reciprocating engines. In general aviation aircraft, the modern horizontally opposed engine is most commonly used. With its smooth operation and small frontal area, it has become the standard of the industry. These general aviation aircraft are used on relatively short flights, where the advantage of lower operating costs outweighs the necessity of high speed. Now that we are familiar with the popular configurations of aircraft piston engines, and before we look into their efficiencies, let's answer a question about cylinder arrangement. Question: what is the main advantage of an opposed engine over a radial engine? Does it have a lower weight-to-horsepower ratio? Is it easier to streamline? Or does it use less fuel? The frontal area of a radial engine is its downfall. The horizontally opposed engine is easier to streamline because of the flat arrangement of its cylinders. At this point, let's turn our attention to the way power is measured and to the many factors that affect engine power. When expanding gases in the cylinder exert a force on the piston head, the piston is forced down. The number of pounds of force applied to the piston and the distance it moves give us the number of foot-pounds of work performed on each power stroke. By knowing the number of foot-pounds of work per power stroke and the number of power strokes per minute, we can easily determine the amount of engine power being produced. As an engine undergoes engineering tests, the actual cylinder pressure is measured with special laboratory instruments. This pressure is then used to calculate indicated horsepower. Indicated horsepower is the power actually being developed within the cylinders. Another engine test is made on a dynamometer. This equipment measures the brake horsepower, or the power actually being delivered to the propeller. This brake horsepower is always less than indicated horsepower by a factor called friction horsepower. This is the power that is used to turn the engine and compress the fuel-air charge. In order to measure the performance of an engine, we need to look at some of its efficiencies. In this way, we can compare one engine or one type of engine with another. There are 3 main efficiencies to understand. These are mechanical, thermal, and volumetric efficiency. The mechanical efficiency of an engine is basically the ratio and amount of brake horsepower delivered to the propeller as compared to the actual amount of power produced in the cylinders. For most aircraft engines, this runs around 90%. But the thermal efficiency of an aircraft engine is not nearly as good. This ratio is the amount of heat energy converted into useful work as compared to the amount of heat energy actually contained in the fuel. In this case, only about 30% of the heat energy contained in the fuel is converted into useful work. The rest is lost through the exhaust or is carried away by the cooling or lubrication system. Rather than using the thermal efficiency of the engine, a more commonly used measure of efficiency is the brake-specific fuel consumption. This factor is the number of pounds of fuel burned per hour to produce 1 brake horsepower. This varies from about 0.4 of a pound to around 0.6 of a pound per hour, depending on the speed and the load on the engine. Finally, the volumetric efficiency of the engine is the ratio of the amount of fuel-air charge that actually gets into the cylinder as compared with the volume of the cylinder. This is the only one of the three efficiencies over which we have much control. With all things being equal, the more fuel-air charge we get into the cylinders, the more power we can produce from the engine. Valve timing is one of the most important things that affect volumetric efficiency. During the intake stroke, the movement of the piston from the top of the cylinder to the bottom occurs. But the intake valve stays open much longer than this. It actually opens about 15 degrees of crankshaft rotation before the piston reaches the top of its exhaust stroke, and remains open until the piston is about 60 degrees up on the compression stroke. Both valves remain closed through the remainder of the compression stroke, and until the piston is down to within about 60 degrees of the bottom of the power stroke. By this time, most of the energy has been extracted from the expanding gases, and the exhaust valve opens to allow the remaining pressure to force burned gases out. This valve remains open until after the piston has passed over the top and has moved down about 15 degrees on the intake stroke. Both the intake and the exhaust valves are open for a few degrees as the piston passes over the top of the stroke. This is called valve overlap and is extremely important in determining volumetric efficiency. The volumetric efficiency of a naturally aspirated engine can never reach 100%. This is because of restrictions to the flow of air. However, by using a supercharger to compress the air before it enters the cylinders, we can increase the volumetric efficiency of the engine to more than 100%. Now that we know how to measure engine power and are familiar with the various efficiencies of the engine, let's look at a few more factors that affect engine power. To begin with, there are two instruments that provide an indication of how much power an engine is producing. The first instrument is the tachometer. This tells the engine speed, which is directly related to the number of power strokes per minute. The second instrument is the manifold pressure gauge. This shows the amount of pressure in the induction system. It is measured in inches of mercury absolute, which is the actual pressure of the fuel-air charge before it gets compressed. The pressure inside the cylinder before ignition is determined both by the manifold pressure and the compression ratio. This is the ratio of the volume of the cylinder with the piston at bottom center compared to the volume of the cylinder with the piston at top center. The cylinder pressure is limited, however, by the detonation characteristics of the fuel. This means if the pressure gets too high on the mixture during combustion, it will explode or detonate rather than burn smoothly. This explosion produces extreme pressure inside the cylinder, causing damage to the engine. Another factor which has an effect on the amount of power the engine will produce is ignition timing. If the spark occurs too early in the cycle, the pressure will oppose the piston moving upward, and if the spark occurs too late, the efficiency of the expanding gases will be reduced greatly. Most engines have their ignition timed so the spark will occur when the piston is approximately 30 degrees of crankshaft rotation before top center. When the mixture is ignited at this point, the pressure will continue to rise until it reaches its maximum when the piston passes top center. At this moment, the maximum amount of push will be exerted, and it is at this point the power will be the greatest. One final factor which has a direct effect on the amount of power an engine will produce is the back pressure of the exhaust system. Since exhaust mufflers are essential for noise abatement, They do create back pressure, but the trade of comfort for this reduction in noise level of the engine makes the loss of power an acceptable compromise. Exhaust-driven superchargers, or turbochargers as they are called, also create a power loss due to exhaust back pressure, but here again the power gained by compressing induction air before it enters the carburetor more than compensates for this loss. Let's take a moment and review what we've learned with a couple of questions concerning power production. Question: where is the piston when the exhaust valve opens? Is it before top center on the exhaust stroke or before bottom center on the power stroke? The correct answer is before bottom center on the power stroke. The exhaust valve opens when there is still pressure from the expanding gases in the cylinder to start the exhaust gases flowing out. Finally, where is the piston when the ignition spark occurs? Is it after bottom center on the compression stroke, before bottom center on the intake stroke, or before top center on the compression stroke? The correct answer is before top center on the compression stroke. The mixture is ignited when the piston is moving upward and is about 30 degrees before top center on the compression stroke. As we have seen, there must be a way of monitoring the performance of an aircraft engine, and these instruments do exactly this. The tachometer measures the engine speed in revolutions per minute. The manifold pressure gauge shows the absolute pressure inside the induction system. The relationship between the RPM and the manifold pressure gives a good indication of the power the engine is developing. The oil pressure gauge shows the oil pressure at the bearings. And the oil temperature gauge indicates the oil temperature as it enters the engine. The fuel flow meter is actually a pressure gauge that indicates the pressure across the fuel injector nozzles. Because these nozzles are of a fixed size, the pressure across them is directly related to the flow through them. The temperature of the exhaust gases is measured by an exhaust gas temperature probe as they leave the cylinder. This gives a good indication of the burning efficiency of the fuel-air mixture. Most exhaust gas temperature indicators do not have the degrees of temperature marked on the dial. This is because it is the change in temperature as the mixture control is moved that is important, rather than the actual temperature itself. In the first part of this training program, we have studied the principle of the transformation of chemical energy into mechanical power, the evolution of the aircraft engine, the efficiencies of an engine, factors which affect power, and the instruments used to monitor engine performance. In Part 2, we will discuss the 7 basic systems of an aircraft engine. In part one of this presentation, we discussed the theory of energy transformation, evolution of the aircraft engine, efficiencies of an engine, factors which affect power, and instruments used to monitor engine performance. In this second part, we will discuss the 7 basic systems of an aircraft engine. An aircraft engine is a highly complex device, but as with most complicated mechanisms, when it is broken into systems and each system is studied separately, it becomes easy to understand. The mechanical system of the engine is the easiest to understand. It consists of the crankcase, cylinders, and their moving parts. The engine cylinder is where all the action takes place. Here, a mixture of fuel and air is taken in, compressed, and ignited. As these gases expand, they cause the piston to perform work. The barrel of a cylinder is usually made of high-strength chrome molybdenum steel, with special cooling fins cut around the outside. A cast aluminum head is normally screwed and shrunk onto the barrel. Here again, cooling fins are cast into the head, with extra deep fins on the side with the exhaust valve. This is because most of the heat is on this side. The inside of the cylinder barrel may be plated with porous chrome. This special surface contains thousands of tiny cracks which hold oil to lubricate the piston during operation. Chrome-plated cylinders are commonly identified by a band of orange paint around their base or by painting some of the fins orange. Other cylinder barrels have their walls case-hardened by a process known as nitriting. These cylinders are identified with blue paint. The pounding action of the valves and the flow of hot gases would soon wear away the soft cast aluminum of the cylinder head, so steel or bronze valve seats are shrunk into place. Either bronze or cast iron valve guides hold the valve stem in place. This provides a bearing surface, allowing them to slide back and forth. The piston forms the movable wall of the combustion chamber. This component must be strong enough to withstand all of the forces from expanding gases and must form a tight seal inside the cylinder. The underside of the piston head is usually finned. This allows heat to transfer from the piston into the oil. Cast iron compression rings are fitted into the top grooves of the piston. This provides a seal for the transfer of heat from the piston to the cylinder. An oil control ring is also fitted into the groove below the compression rings. This ring controls the amount of lubrication between the piston and the cylinder wall. Holes are normally drilled through the piston in the oil control ring groove. This allows the excess oil to drain back inside the piston. Some pistons are also fitted with an oil wiper ring. This ring is on the bottom, which either wipes oil toward or away from the oil control ring, depending on the engine design. Piston rings must be carefully matched to the cylinders. This is done so that either the ring or the cylinder wall will wear just enough to form a good tight seal. Hard chrome-plated rings may be used in cylinders having plain steel barrels, but only plain cast iron rings may be used in chrome-plated or nitrited cylinders. The piston is held onto the connecting rod by a hollow, high-strength, highly polished steel wrist pin. This pin, in almost all aircraft engines, is free-floating, meaning it is free to rotate in both the connecting rod and the piston. The wrist pin is prevented from scoring the walls of the cylinders by plugs of soft aluminum or brass, which are inserted into each end. Another component, the connecting rod, is forged of high-strength alloy steel. This rod changes the up and down motion of the piston into the rotating motion of the crankshaft. The smaller end of the connecting rod is fitted with a pressed-in-place bronze bushing. This bushing rides on the wrist pin in the piston. The larger end of this rod is fitted with a removable cap and a two-piece bearing insert. This allows the rod to ride on the polished journal of the crankshaft. The real backbone of an engine, however, is the crankshaft. This high-strength alloy steel shaft is hollow to reduce weight and to provide an oil passage. Many crankshafts have sludge tubes pressed into their throws. Then, as oil flows through the spinning shaft, any sludge contained in it is slung to the outside of the tube, where it is held until the engine is disassembled at overhaul. The bearing journals are highly polished and ride in soft bearing inserts in the crankcase and connecting rods. The number and arrangement of the cylinders dictate the type of crankshaft the engine will have. The popular four-cylinder horizontally opposed engine uses a four-throw 180-degree crankshaft. This means when piston number 3 is on top of its compression stroke, number 1 piston is at the bottom of its compression stroke. The firing impulses are all 180 degrees apart, and all 4 cylinders fire in 2 revolutions of the crankshaft. The crankshaft for a 6-cylinder horizontally opposed engine has its throws forged so no 2 are in line. This means that a throw brings its piston to top center every 60 degrees of crankshaft rotation. The firing impulses occur 60 degrees apart from each other. When cylinder number 1 is at the top of its compression stroke, number 4 is moving outward and is 60 degrees away from top. Number 5 is 30 degrees from bottom and moving down, meaning it will have to travel 120 degrees before it reaches top center again. It is interesting to note that the crankshaft of a radial engine has only one throw, and a master rod connects one of the pistons to this. All other pistons connect to the master rod through link or articulating rods. Each alternate cylinder fires in turn, which means all cylinders fire in 2 revolutions. At this point, let's take a look at the resonant frequency of the engine as it operates. Here, vibrations of both the engine and propeller at certain engine speeds will cause damaging vibrations. To prevent this, counterweights are usually installed on loose-fitting pivots and allowed to freely rock back and forth as the crankshaft spins. The oscillating action of these counterweights changes the resonant frequency of the rotating mass, so that it will not be excited by the firing impulses in the normal operating range. Now let's examine the propeller. This unit must absorb all of the power developed by the engine, and because of this, it must be rigidly attached to the crankshaft. To secure the propeller tightly, early engines used a tapered crankshaft fitted into a steel propeller hub, which was locked with a single steel key. On later model engines, a splined propeller shaft was used. Today's modern trend of engine construction, however, is to use a crankshaft with a flange, forged as an integral part. Since an engine develops its maximum power only at high speeds, the propeller may actually turn too fast, which will cause it to lose efficiency. To solve these difficult problems, many engines drive the propeller through a reduction gearing at about 1/2 of the crankshaft speed. In most cases, the simplest reduction gearing is the spur-type gear. But when more power must be carried to the propeller than can be transmitted with the simple gear arrangement, planetary gears may be used. This arrangement keeps the propeller shaft concentric with the crankshaft and does not reverse direction between the two shafts. Now let's look at the main body of the aircraft engine. This is the crankcase, which is made of cast aluminum alloy. This component houses all rotating parts of an engine. The cylinders attach to it and become the actual point where the engine is mounted in the airframe. In the crankcase, a pump is used to force oil through drilled passageways to lubricate crankshaft bearings through bearing supports. These bearings use soft metal inserts mounted in a steel shell that fits into the bearing supports to hold the crankshaft centered. Thrust loads are carried in some engines by a flange on the bearing, riding against a polished thrust face on the crankshaft. In other types of engines, ball bearings riding in deep races carry thrust loads into the crankcase. The crankcase is designed to have sufficient rigidity to hold the crankshaft and camshaft in perfect alignment for their smooth operation. All of the accessory drive gears are mounted in the rear of the crankcase. The mark teeth on the camshaft drive gear are designed to mesh with mark teeth on the crankshaft gear. This is done to assure proper timing of the valves relative to crankshaft rotation. In Part 1 of this program, we discussed volumetric efficiency. To maximize this factor, the valves must open and close at just the right time during the cycle of events. This critical timing is accomplished by the shape of these cam lobes. As the valves are pushed open by the rocker arms and the push rods, the cam followers ride up on these lobes. Then, as the cam followers ride down on the opposite side of these lobes, the valves are closed from the pressure of the valve springs. Another problem associated with engine operations is that of expansion caused by the excessive operating heat range. Here, when the engine heats up, the cylinders expand more than the push rods, causing the clearance between the rocker arm and the valve stem to increase many times what it was when the cylinder was cold. As a result, valves using solid valve lifters are timed to open properly when the engine is hot. This means the engine has very low volumetric efficiency when it is cold, usually causing rough idle. Another problem is abnormal wear of the components in the valve train due to excessive clearance at operating temperature. To prevent this wear and maintain a constant valve timing regardless of the dimensional change of the cylinders, hydraulic valve lifters are used in almost all horizontally opposed engines. As you can see, the plunger fits into the lifter body with a slight clearance. This allows a calibrated oil leak. When the valve is closed, however, the spring raises the plunger and oil from the engine flows into the body through the check valve. Now, as the cam pushes up on the cam follower, the check valve seats, trapping the oil in the body and forcing it to serve as a link in the valve operating mechanism. By using hydraulic valve lifters, we are able to maintain zero clearance in the valve train. This improves volumetric efficiency when the engine is cold, and since there is no lash or space between the moving parts, there is very little noise or wear in the valve train. With radial engines, a little different arrangement is necessary. This is because a radial engine has all of its cylinders in a single row, so a camshaft would not be practical. Instead, a cam ring or plate is used to open the valves. Also, all radial engines use solid valve lifters, and so there must always be a small clearance in the valve mechanism. The rocker arms are fitted with rollers that contact the valve stem. This minimizes the wear from the repeated hammering. Here, the valve mechanism is lubricated by oil forced into the rocker boxes through the hollow push rods. This oil merely drains back into the crankcase through the push rod housings. The valve clearance in a radial engine equipped with solid valve lifters is usually set with an adjustment screw on the rocker arm. But since opposed engines using hydraulic valve lifters maintain zero clearance in the valve train, they have no need for this adjustment. The valves used in all modern aircraft piston engines are of the poppet type that close against a steel or bronze valve seat in the cylinder head. The stem slides back and forth in a bronze or cast iron guide. Exhaust valves on some engines are hollow and partially filled with metallic sodium. When this type of valve is at operating temperature, the sodium actually melts, and as a liquid, it sloshes up and down to pick up heat from the valve head. This heat is then carried into the stem, where it is dissipated through the valve guide into the cylinder head. At this point, we are about to leave the mechanical system of the engine. But before we do, let's review the material we have studied. Question: what is the purpose of the metallic sodium in some exhaust valves? Is it to aid in cooling the valve, to increase wear resistance of the valve stem, or to provide an abrasion-resistant valve face? The correct answer is to aid in cooling the valve. Some exhaust valves have hollow stems, partially filled with metallic sodium, to aid in transferring heat from the valve head into the stem, where it can be carried into the cylinder head through the valve guides. The mechanical system of an engine is the most obvious of all the systems, but equally important is the lubrication system. For the most part, the lubricant flows through the engine to reduce friction, remove heat, and provide a seal between moving parts. Most oils used in modern piston engines have a mineral base and may be either a straight mineral oil, which is normally used for the break-in period of new engines, or an ashless dispersant oil that has additives to prevent the formation of sludge. Ashless dispersant oils are the most popular oil in use. If the entire oil supply is contained in a sump attached to the engine itself, the engine is said to have a wet sump lubrication system. But some engines require more oil than can be stored inside the engine. This is why a dry sump system is used predominantly in radial engines. In this system, the oil is stored in an external reservoir. It flows by gravity to the pressure pump, and after circulating through the engine, it is returned to the tank by a scavenger pump. The pumps used in lubrication systems are all constant displacement types. This means they move a fixed volume of fluid each revolution. The more popular configuration of this type is the gear pump. This unit has two spur gears that rotate inside a close-fitting housing. Oil is picked up as the teeth separate, carried around the outside of the gears, and is forced out into the system as the teeth mesh again. Since the output of a constant displacement pump varies with its speed, a relief valve must be used to maintain a constant pressure. This allows enough of the pump's discharge to be directed back into the input to keep the output constant at the desired pressure. As the oil flows through the engine, it picks up heat from the bottom of the pistons, cylinder walls, and all of the moving parts. This hot oil then flows through an oil cooler where the heat is transferred to the air flowing through it. If oil leaving the engine does not require cooling, it automatically bypasses the cooler and returns directly to the sump. Contaminants picked up along the way by the oil are held in suspension until the oil passes through a strainer or filter. It is here they are trapped and held. Since almost all engines have a simple screen to remove contaminants before the oil is pumped through the engine, a simple bypass is installed to allow oil to flow around this screen in the event it is plugged. The reason for this is that it is better to pump contaminated oil through the engine than no oil at all. Filtering or cleaning of the oil is best accomplished with a cellulose-type oil filter. This will remove contaminants far smaller than the simple screen we have discussed. Cold weather presents a problem for the lubrication system. In fact, the oil may become so thick that the engine becomes hard to start. To help solve this problem, it is recommended that before the engine is shut down, some gasoline directly from the fuel system be mixed with the oil to dilute it. This diluted oil provides adequate lubrication for starting, and the gasoline will evaporate out as the oil warms up. Before we leave the subject of lubrication, let's take a moment to review. Question: what type of oil is normally used for braking in an engine? Is it straight mineral oil or ashless dispersant oil? The proper oil to use for braking in an engine is straight mineral oil. Tests have shown that ashless dispersant oil does not allow enough wear to properly seat the moving parts of a new or freshly overhauled engine. As we learned in Part 1 of this program, approximately 70% of the heat energy in the fuel is wasted, and much of this waste must be carried away by the cooling system. There are two types of cooling systems, usable for aircraft engines. The first was liquid cooling, used during World War II. In this instance, waste heat was absorbed in a liquid and carried outside the airplane, where it was given up to the air by means of a radiator. But the more popular system today is air cooling. Here, cylinders are finned to increase their surface area, and air flowing over them absorbs the heat directly. In a low-powered engine, enough heat can be removed from the cylinders by simply allowing the air to flow over them. In higher-powered engines, however, pressure cooling is required. In these cases, ram air is sent into the compartment above the engine and flows through the fins to an area of low pressure below the engine. To control this low pressure, cowl flaps are used to direct the air through the fins. Around areas of the cylinder that have an excessive amount of heat, such as near exhaust valves, the fins are made extra deep to provide more surface area for cooling. To force air to flow through these fins, intercylinder baffles made of thin sheet metal are installed. And seals prevent air from escaping any other way. The next system we'll examine is the fuel metering system. Since the amount of power an engine can develop is directly related to the amount of heat energy that can be released from the fuel, it is the primary function of the fuel metering system to help provide the right conditions for the maximum release of this energy. The fuel metering system may be either a simple carburetor or a fuel injector. In either event, the system has four essential functions. First, measure the amount of air to determine the proper amount of fuel needed for the engine. Secondly, since liquid fuel will not burn by itself, this metered fuel must be broken down into tiny droplets or atomized, and finally vaporized. This vaporized fuel is then mixed with the air entering the engine and uniformly distributed to all of the cylinders. The induction system of an aircraft must supply an adequate amount of filtered air to the cylinders so the energy can be released from the fuel. For this reason, an air filter is used to remove impurities from the air before it enters the engine. It is extremely important that this air be perfectly clean, as airborne abrasives can cause severe engine wear. When fuel changes from a liquid into a vapor inside the carburetor, enough heat is absorbed to cause the formation of ice. To prevent this, an air valve in the induction system is used to direct hot air from around the exhaust into the carburetor. This warm air, however, is not filtered. Fuel-injected engines are not as susceptible to carburetor ice, but the air filter may often ice over when flying in freezing rain. So, on this system, an alternative air valve is installed, which can be opened to allow warm air from inside the engine compartment to flow into the fuel injector. Another important system is the exhaust system. While it is not considered to be one of the power-producing systems of an engine, it is important as a power-conserving system. Because of the extremely low thermal efficiency of an aircraft engine, we lose much of the heat energy of the fuel directly through the exhaust. Therefore, this system must withstand the high temperatures of the energy-rich gases flowing through it, while creating a minimum of back pressure or opposition to the gases leaving the cylinders. The exhaust noise of aircraft engines is reduced by mufflers. Thin sheet metal shrouds surround the muffler to force air passing to the cabin or carburetor to flow over the surface of the muffler. This not only reduces noise levels, but also provides cabin heat and heat for induction air. Some of the energy in these gases may be recovered by installing a turbocharger. When only a limited amount of supercharging is required, most of the exhaust goes out the tailpipe through the wastegate. But as more supercharging is required, the wastegate closes, forcing more of the gases through the turbine, which spins the compressor faster to increase the manifold pressure. The final system of an aircraft engine is the ignition system. This system provides the hot spark needed to ignite the fuel and air mixture inside the cylinder. All modern aircraft reciprocating engines use a magneto to provide high voltage for the ignition spark. This unit is a completely self-contained alternating current generator with a set of interrupter points and a step-up transformer. The magneto is geared to the engine and timed to produce a spark that will occur the instant the piston is in the correct position for the mixture to be ignited. The high voltage built up inside the magneto is directed to the proper cylinder by the distributor and is carried to the spark plug by a special high voltage shielded ignition lead. Inside the cylinder, the high voltage merely jumps to ground between the electrodes of the spark plug and causes a spark of sufficient intensity to ignite the compressed fuel-air mixture. At this point, we have finished our discussion of all 7 of the basic systems of an aircraft engine. So let's take a moment to review the material we have studied. Question: what is meant by a wet sump engine? Is it an engine which uses a liquid lubricant, an engine which uses an external oil tank, or an engine which carries its oil supply inside the engine? The correct answer is A wet sump engine carries all of its oil supply inside the engine. Finally, what drives the turbocharger compressor? Is it driven by an exhaust-driven turbine, or is it gear-driven from the engine? A turbocharger compressor is driven by an exhaust-driven turbine. Spinning the turbine causes some back pressure, but the loss is more than regained by supercharging. The aircraft reciprocating engine is one of the most dependable engines in our modern transportation system. With proper servicing and maintenance, it will produce its power with the dependability that has been built into it.